All right, it's time for another brainstorming session. This is something I wanted to talk about last time, but I ended up spending my whole time just working through the ideas on the story graph sort of execution model stuff, the stuff I call the story machine. And the other half of what I wanted to talk about is sort of intermingled with that, but it's going to end up all being here. And that's how some thoughts I have about how editing story graphs is going to look in the future and how it might be able to look better now. And there's a big main concept I want to keep in view for this brainstorming session, which is I'm not trying to think of like magical features or something, right? So that's something that's cool you can do when you're building an editor, right? If you build a text editor for text or a node and wire editor for story graphs or whatever else you've got, you can think of really cool magical editing features, things that automatically do cool layout, help you find what you're looking for quickly, navigation features, project management features, all of that. That's not what this is going to be about, though. Instead, I want to think about something a little bit closer to what I'm designing right now, which is the data structure. And there are ways that the data structure can impact what is possible or what is easy in the editor in terms of what magic you can provide and what you can't. And so those are worth looking at. But there's also another way that the data structure design impacts how you work with the data once you're in the editor. And even when you're outside of the editor, now in my hacked way of looking at this stuff, this matters. And it's a little hard to explain to someone who doesn't know what it means exactly, but it's the idea of like working with the data. And obviously that's on the surface level a thing you need to be able to do. You need to work with the data. But what I sort of mean is, what is the workflow like? How are there options for gracefully moving between likely states that would show up in sequence during a project? So an example of this, it will probably help. So let me throw a picture up here that will clarify what I'm talking about. Okay, so in this image, we have a before and an after. And this is a before and after of what this might look like in a visual editor, sort of sketched up. You can see we have a single graph in the before case, and then in the after case, we still have that same graph. So graph one is in before and after, but a big chunk of graph one has now from the before, a big chunk of graph one from the before slide has been relocated. It's gone to live as a part of graph two. And then in its place, graph one now has this node G2, which is meant to stand for sort of a reference to the new graph that's been added in the after slide. And the graph 2 is basically sort of that chunk of the graph that's been pulled out with some port nodes around it. So by port node, I mean those like the ones labeled alpha, gamma, and lambda on the edges there. They don't stand for the idea of content here. They're standing for the idea of sort of abstraction boundaries. So alpha is an entry point, but with no content, as it's meant to be this boundary where you are entering into a chunk of graph where there were two possible entry points. And so a sort of dummy entry point fills in the spot, and then you have to use this, you would have to push the graph and select one of the initial paths into the graph. And the outgoing ports are abstract so that this new thing that's been pulled out is now abstracted from its original context. It could still be that you're only ever going to link up the gamma to the thing labeled Y and the lambda to the thing labeled Z, but it could also be that you're going to link them up to other parts of the larger graph now that they're abstracted. It could be reused, sort of the way a function can be reused. I'm hesitant to boil this down to just function calls, but now that there's a graph stack, it's getting more and more similar to function calls. I just don't want to fully put myself in the mindset of thinking of it as a call when it might not entirely be that in the final thing. There are a couple of different flavors of the graph stack that I'm still playing with, but now we're getting into the compute model. Let's ignore that part of it for now, or only talk about it as it's relevant. So the bigger topic here is this transformation is a pretty critical one with this data structure that I am building. And the reason I say that is because it is very analogous to other data structure transformations that I have seen be critical in programming in C. So this is very similar to the idea of like you have a big struct with lots of members, and then you notice that a certain segment of those members all kind of belong together as a group, and you want to pull them out. And generally you do this because one, you either want to apply some operation to all of them together. So for instance, if I have a big struct and some of the members need to get cleared to 0 together, I might throw them together into a struct that is then that is outside, like a smaller struct, and then make that smaller struct a member of the original one, so that I just have that clear to 0 option. But also, and probably more often, you pull that thing out so that you can reuse it, or so that you can have more than one of them inside the original big struct, right? So you pull things out as this sort of step towards using that content in a new way. Taking something you wrote when it was just a piece of a bigger picture, and then taking those pieces and reorganizing them. And I think thinking about this as reorganizing is going to be critical. So there's these operations, and the same thing also applies, by the way, to functions, right? I pick structs as the C example there, but code that you execute has the same thing happen, where you have a block of code or a couple of lines of code that need to end up being reused, and so you try to pull them out as a function. And in the process of doing that to code, it's important that the data structure you build and the way you intend to edit it works that way, because that's a very critical operation. That is what allows you to build something incorrectly on day 1 from the perspective of day 2, but still make progress, right? So there's a way to make a really bad kind of editing experience, which is that you can construct with your editor any possible artifact of the editor, right? So an artifact of the editor is something that could come out of that editor. And so if you think of like, what's the data structure this thing is editing, ideally the editor covers all possible rearrangements of that data structure that are valid. So if there's some valid version of that data structure you want, there's some way to build it in your editor. But the worst possible situation is that you have to do all of the steps correctly, right? So if I build an editor for a data structure, and it does in fact let me build any instance of that data structure that I want, but it has the property that if somewhere along the way I do a step wrong, then I'm only going to be able to, the only way to get to the right thing will be to do a lot of backtracking or a lot of other slow manipulations to unconnect things and reconnect them, or unwind how I built it and build it up a different way, right? If any of that is necessary, then if I make partial progress on day 1, then on day 2 I look at it and go, okay, what I really need to do now is to take these parts and reorganize them a little differently and use them in more dynamic ways than I did on day 1. So it's sort of like if I have some members in a struct and I pull them out and then I make it a list instead of a single copy of those members, right? So if I started off with, I've got this bundle of 3 related members and they're just flat here, they're members of the struct directly, and then I decide I actually want an arbitrarily long list of those 3 members. So maybe what I want to do is pull them out into their own struct and then make a list of them in my bigger struct, right? And if the only way to pull them out is to untangle the whole big struct, right? And this might sound silly, like why would you need to do that? But you could imagine a bad design for a type system, like say that you, instead of, right now when you write a struct in C, what you do is you just list, here's the type of a thing, here's its name, here's the type of another thing, here's its name, and so on and so on. But imagine you also had to set the offset of each one, right? So you say, here's the type of this thing, here's the name, and I want this to live at offset 0 exactly. And here's the type of another thing, and here's its name, and I want it to live at offset 8 exactly, and so on for every member. On day 1, you could lay out your struct correctly, so long as you understood the size of all your types and that you were using as fields. It wouldn't be a big problem. But on day 2, if you went to pull out a couple of those members and replace that spot in the struct with a list, you might then find yourself also having to readjust the offsets of everything afterwards, and also readjust the offsets of the members you pulled out inside their new context. So all of that offset data that you're being forced to encode in this alternative type system I'm talking about here would get in the way of the exact thing I'm trying to talk about, which is it would bake into the data structure a thing where the transformation from the before to the after requires a lot of reworking, like a heavy amount of changing of the decisions that are made inside the data. And that means that the editor has to do a lot of work to do this kind of reorganization. And just as an aside, let's talk about why I'm so keen on these reorganizations. I've already said that it's because it's this common operation that comes up. So just because it's common, that is a good reason to think about it in the sense of if it's going to be common, then it shouldn't be expensive, or else you're going to have a common operation that takes you a long time. And that's not what you want. That is going to mean that doing things with this will not really work out well. It's going to take too long to get big stuff done. But there's another part of why it's important, which is why you can't do without it, right? So I said it's common, but I also got to the conclusion that it's common by saying that this is how you work. On day 1, you make some progress by doing something that is useful progress, but that is wrong from the perspective of day 2, and then you have to change that. And you change that by first, it's like a 2-step process. The first step is to not change any of the actual structure or behavior of how things work in a meaningful way, but just to reorganize how things work, right? So that's the pulling out the struct part. So usually what I would do if I was going to replace a single chunk of members with a list of those same members in a larger struct is first I would pull them out and make sure everything works the same way as before, but just with this extra struct in the way, right? So first I pull out the members into a struct, and then I get things building again with that change in the organization, but none of the logic changes. And then I would turn it into a list. Now, sometimes when you're moving quickly, you skip the middle step, you do the reorganization, but you don't get it working like it was before. You just do the reorganization and go straight into transforming the full structure around this new organization. But the only reason you do that is because either one, you weren't at a working state beforehand anyways, like you're doing a deeper refactoring, or 2, because you're so confident that it's a trivial transformation that it feels like a waste of time and you don't even think to do it, right? So in those cases, you are still doing this first step of sort of pivoting the organization aspect while holding constant the main behavior or the meaning of everything from the outside, right? When this thing is inspected as a piece of running software or as a piece of content, it looks the same to a end user, but to you, you've pivoted the organization, and then you switch it and you hold constant the main organization, but you update the behavior itself and the logic around by utilizing the new feature of the organization that you've created, right? So that 2-step process of holding the behavior constant or holding the meaning constant while reorganizing, and then pivoting to holding the organization constant while changing the meaning of things a little bit or a lot, that is an extremely important tool to allow this process where what was useful to do on day 1 but wrong on day 2 isn't a waste of time, right? If I set up a system where I have to do something correctly on day 1 from day's 2 perspective before I can do day 2, then it means that inductively fills out the entire length of the project. If I have a 100-day project, I have to know I have to execute perfectly at every day. And whatever day I make a mistake, however many days I go past that before I realize it's a mistake is how many days I have to redo after I've unrolled and gone down a different path, right? Whereas if you have this ability to reorganize that is not too expensive, then you get different options. Now, we're not in the critical worst case right now. I already, in my data structure, just because I have the graph stack, I have the ability to reorganize. But if the ability to reorganize is too expensive, I won't do it except in the absolute necessity cases. I'll avoid the reorganization steps, and I think this would lead to sort of bad maintenance. What's the word I'm looking for? Discipline, right? It gets really hard to do good maintenance discipline if maintenance is an overly difficult chore. So what I want to think about here, what I'm building towards with all of this is, how difficult is it to do the transformation of this kind? Because I have now gotten far enough into the building of this data structure and building of the compute model that I see an opportunity for a reorganization step and a reconstitution of the logic step, right? Changing the organization, changing the meaning, the two-step process of transforming what I did yesterday, which is now wrong from today's perspective, into something useful again without having to undo what I did yesterday. But instead, the key there is that trick of reorganizing without changing what you did is what sort of means it creates the path forward. So you don't have to preemptively know to organize this into two graphs, right? So the picture I have here shows that I went from one graph to two graphs without changing the meaning. This is a reorganization picture. And changing the logic is just a part of editing. That's the meat and potatoes part, if you will. But the reorganization part is the part that you want to feel like is nice and easy. It sort of feels it feels rote. It feels like something a computer really should be helping you with. And it will, like I said, we could just kick this can down the road and say, well, this is magical feature land, right? So why I emphasized I don't want to think about magical editing features is because you could look at the problem I'm pointing out here and you could say, well, this is fine, right? Like you're going to just have an operation where you're going to highlight all of these nodes that you want to pull out into graph 2, and you'll have a button that does that. And probably I will. Like that's not a bad idea, but that's kicking the can down the road because right now I'm not designing the editor. And so while that might be there, how I make decisions about the current data structure very likely will impact two things, right? One is how easy or difficult would it be to implement that magic feature? And it turns out from my experience writing text editors and stuff, you can imagine magic features, but you don't always write them if they are extremely difficult to actually get right or to maintain or something like this. And so we have the opportunity now to analyze how this data structure might make this operation so hard that it can't be done at all. But there's another way we could look at it, which is, say we don't have a magic editor, right? Notepad.exe on Windows is not a magic editor in any way. It doesn't do a single bit of magic. And yet you can do a little bit of editing in it. It's the very bare bones idea of what a text editor is, right? It opens a single text file, it edits it. It doesn't do anything in terms of fancy commands. It doesn't do anything in terms of fancy visualization. It doesn't do anything in terms of fancy navigation. It's just the very basic lowest level common denominator of what is a text editor. And I would kind of like to think about this as, what would the simplest data operations that a node wire story graph editor is likely to have? What would those operations feel like to use to manually implement this transformation? Because the more difficult that is to do with direct manipulation using the simplest editing commands, the more I think there's an issue. Okay? So this might come down to what is the data structure once it becomes an editable data structure. Like right now I have this data structure and it is a hacked together data structure, and the final one that goes into an editor, if it does get that far, would maybe have slightly different properties than this one, just because it might be harder to hack together an equivalent data structure, and there might not be any benefit to hacking it together that way. But I want to think it through and see if there's any serious consequences to the differences I might want there, or if there are ways I can adjust the data structure now to make that path in the future more walkable. And then I also want to take the same thinking and also reflect it back onto the hacked version that I'm doing now, because there is an equivalent problem I'm already having as I'm using the system. So as a little update, and aside from this main conversation, I've gotten the compute model now to a point where I'm starting to do some of the stuff that I'm excited for. Like, it's starting to feel exciting to use because the magic of the story engine is just barely starting to ignite in the current iteration. And I still haven't done a whole lot of writing for it. I've written a little more than what I've shown so far on the videos. And you might see a bit more of what I've written in somewhere along the way if you watch enough of this video. But I'm also starting to notice these moments when I think, oh, I should probably actually pull this out, and that way it can be reused in this other context that I see coming up later, or it can be abstracted for these, for whatever reason it seems nice to do it. There are times where it's just, like, I want to not have the complexity of having this all splatted out into one layer. So it's more of a conceptual or organizational tool only. And even then, it's still handy for reorganization operations to not be too bad. And I haven't really stopped and thought about how bad is it for me right now to reorganize with the current way I've hacked together the data structure. And so I also want to take a look at that, but one step at a time. So let's start by projecting into the future the visual version, and then maybe we can spend some time looking at the hacked version, because that might help me during this prototyping phase too. Okay, so I'm looking at this image still, and I'm going to think through what the operations would look like to go from before to after and talk it out. And I'll start with the absolute most primitive picture I've got, and then, maybe go back over it a couple times as I work out alternative views of how this might go. So I'm going to take it as a given that it's going to be trivial to create a new empty graph. So creating graph 2 happens no issue. And it's also, I'm going to take it as trivial to have two graphs side by side and to imagine them sort of on screen simultaneously. So interactions can involve clicking on something in one graph, copying it and pasting it in the other, or cutting it from one and pasting it in the other, or grabbing it and dragging it from one to the other. Those are visual interface operations that are all reasonable to assume. I'm also going to go ahead and assume that there are stuff like selection options that are already good, that are thought through. So like if I want to select B, C, D, E, and F, that might just be as simple as having a rectangle selector, or there might be other ways to build selections, but we're going to assume that getting the selection isn't hard, because that's not a problem of the data structure as much, right? It might be, there might be a case to be made that just because it's a directed graph that I have in a visual layout, that the problem of selection is already hard for the reason that I've selected a particular data structure and a visualization for it that makes selection hard. But there's a second visualization I could imagine that might solve that. So you could also always look at a directed graph as a list of vertices, and then selection becomes just a matter of selecting items out of a list. So like, I'm just going to set that aside, because I think that there's a couple of ideas I have that might get us there. And there's also a lot of thought put into how you would lay these things out. So if you're building one of these, you would probably lay it out manually in ways that made these operations more likely to be easy. So I'm not too worried about it. The more interesting stuff is, let's say I've got graph 1 as it is. I've got an empty graph 2 underneath it, or side by side with it on screen somehow. And I'm going to move those nodes around somehow, right? So the worst case scenario here would be that there is no such thing as transporting data sort of laterally like that. So for instance, if the logic was, hey, when I try to copy the node B, C, D, E, and F and paste them into graph 2, there's no way to copy the edge from A to B or the edge from A to C, or all of those edges leaving from D, E, and F. And so the paste is nonsensical, and it just can't be done. And so then if this was the structure of the editing, the only way you could then do this is to manually create B, manually create C, D, E, and F, wire them up the way they already were, and then put in the alpha and the gamma and the lambda, and then wire them up to match the way that it looks in the after slide, right? So that's worst case scenario. So I'm gonna go ahead and say we're gonna need a story about lateral movement of data between graphs that is flexible, and it might need to be so flexible that it bends our understanding of what counts as a graph, so that intermediate states are possible that would not necessarily make sense as sort of fixed final structure of a thing. So the next image I could imagine is I copy B, C, D, E, and F, and when I paste it into graph 2, what pasting means is we walk all the edges that are there, or all the nodes that are in the list, and it reconstructs an empty node with it reconstructs a new node with each of the same content. So whatever content is in B, C, D, E, and F can be copy pasted. We'll take that as an assumption for this conversation. If it can't be, then there's a whole separate reason why this is not going to work. But if they can all just be copied over as content copies that are trivial to do, then we get the 5 nodes, and then the wires don't show up, right? So it's just a copy of the selected section and nothing else. Right, so if I select the vertices and I copy paste them, then just the vertices move over. And so I just get a graph with 5 isolated vertices, B, C, D, E, and F in graph 2. And then I have to manually do the wiring. So that's still 1, 2, 3, 4. That's at least 4 things, the 4 wires between B and C and D, E, and F. Those 4 wires are definitely things that need to be doable. I think even all of the wires, like so 4, 8, 9, 10, so all 10 wires in graph 2 should probably be things that the translation or transition from one context to another can help us with. But at the very least, those 4 in the middle, because those 4 live in between all of the vertices we are copying. So the next logic there is to say, well, is this a matter of the selection logic that I propose not being good enough? B, C, D, E, and F could be selected along with the 4 edges in the middle, right? All at once. So if it was a visual selection kind of thing, then that still works out just fine given this particular picture. You could also imagine a rule that's just, if you're looking at a list of vertices, then as you're selecting them, it also assumes that the selection expands from the hard selection you get to the graph selection, right? So the hard selection is the selection of items in the list, and the graph selection is items in the list which are vertices plus the edges that are contained, or the edges that have 2 endpoints inside of the selection, right? So what I mean is, like, the edge from B to D, well, it would look and go, this edge B is selected and D is selected, so I'm selected too. Like the edge, I am selected. But the edges that have one of their endpoints is outside of the selection, they wouldn't get picked up. So if it went there, then we're still dropping 1, 2, 3, 4, 5, 6 edges, right? So that's still not even getting us half of the work automatically. or that's got us the node copy, the content copy, which is definitely a big chunk of the work. But in terms of reconstructing the structure that was contained in the graph one, as we are doing this reorganization, there's a lot of opportunity for sort of typos, right? This is akin to like a copy paste bug, where if I'm moving stuff from one place to another, as I'm trying to hold the meaning constant and just reorganize, but in the process of doing that move, I accidentally wire these things up just slightly wrong. Then I've broken that rule that I was trying to follow, that I was holding the meaning constant while I was doing the reorganization. Okay, so having thought all that through, and I apologize if it seems like I'm getting slow to the point here. I'm really just wrapping my head around what's good enough and what's not. I think I'm coming to the conclusion, though, that the only thing that's good enough in terms of moving the content from graph 1 to graph 2 is that when I select B, C, D, E, and F as a sort of subgraph that I want to move, and I click and drag it over, it needs to understand that all of the edges connected to B, C, D, and F, even if they're only connected on one side, need to show up somewhere in the new graph. And so I think what I would want then, thinking about this and looking at it, maybe the best thing would be that when you're doing something like that, those nodes called alpha, gamma, and lambda might just be automatic. That's one option, right? So it might just be that when you do that, it automatically understands that it creates all of the same pattern as before, including the ports. So alpha, gamma, and lambda, when I call them ports, it's because I'm thinking of them as the inputs and outputs that are abstracted. So there's an input side here where it's a node in the graph, but it's not meant to be a place where you land. It's meant to represent the boundary of how you get into the graph. And the same thing on the outside, like the outgoing end. And so when you copy paste B, C, D, E, and F, what it would do is it would look at, okay, any edge here between two nodes that are selected will just go to the nodes that are copies of those selections. And the contents on those edges can also just go into those, right? So that those just become directly mapped. The edges that connect on only one side that are incoming will still be capped with the same content, but the edge will have a new initial side vertex. So the vertex that goes on, or the story state, I could say, that goes on the beginning side of the path, isn't getting copied with everything else. So instead we put in a dummy. We put in a blank node. We just put in a blank node there to make the structure make sense, but we don't move the content because that wasn't a part of the selection. And same thing with all of the outgoing edges that are outgoing from one of the selected vertices, but that don't arrive at another selected vertex. So things that leave the selected subgraph, those go to a port that it becomes an empty state that you drop in as well as you're pasting. So I think that's the best story I can come up with for how a copy paste there would need to work. But let's keep going. So there's a little bit more here. The next question that we should get into is that an algorithm that is extremely difficult, annoying, or fine, or actually easy, right? Like there's a range there, and I think I'd have to go and start implementing that to find out. My intuition is that this would be like fine or maybe annoying, right? It's doable. I don't see any reason why there's not like magic references here that need to be recomputed, GUIDs that need to have special logic applied. The content, if we're assuming content on all of the nodes, and states and paths are both nodes as a reminder, if the content on any node is trivial to copy into another node, then I think the graph copy is annoying but fine, and that's probably good enough. The other piece of this is, what if it's not just a copy? Because so that gets us to the point where we've reconstructed the subgraph pretty nicely on the graph 2 side. And then a little bit of work does need to be done, because even though those abstract nodes got dropped in there as dummies, you would want to put in stuff like, okay, well, when you arrive at gamma, that needs to pop the graph, right? So this becomes a pop, and you wouldn't want that to be automatic. That's the popping of the graph is semantic compute level stuff that you should have to put in. That'd be like saying that if my text editor sees that I'm copying and pasting a block of text into a new spot out into a spot in the text file that isn't a function, it should automatically put a return at the end, because it needs to treat this as a new function. You don't want the content automatically magically changing. Not in a notepad case especially, but I do think you want the notepad case to at least have a useful copy paste. Now, another thing that could take this even further to make it more useful is to think of it as cutting and pasting. And cutting and pasting would be how you'd implement something like dragging it and dropping it too. So if I selected them all, one picture you could have. So let's go down a wacky road for a minute. One picture you could have is that you select a node or a set of nodes, and you're going to drag them from graph 1 to graph 2. And that the edges between graph 1 and graph 2, or the edges that were not fully contained inside the subgraph, that were half contained in the subgraph, would stretch across graph 1 and graph 2. And you could do that, and what that would mean is that you've created a situation where these graph boundaries can be violated in the editor, and so they're actually, I wouldn't want to make a situation where you couldn't save until you'd finished changing things. So you'd have to split your data structure up into sort of two modes. There's the full mode where anything can happen, including edges crossing between graphs. And then there's the version of, there's some of those are quote unquote valid, or something like that. And you'd say okay, in order to pass a graph through the compiler, it has to be valid. It can't have any edges that leave or enter the graph. The graph boundaries have to be respected by all of the edges. It does lead to some other questions, like, does that mean the graphs no longer own the edges that are inside them? Right now, my memory management thinks of each graph as sort of a large data structure with the list of all of the nodes inside of it. But if an edge can leave one graph and go to another inside the data structure, you would end up with situations where neither graph could exclusively claim to own it, and you'd have to make a rule or something like, whichever graph it starts from owns it. But I think that leads to other problems. Maybe it would have to be that nodes aren't owned by their graphs at all. They're only referenced by it, like they're indexed into it, but they're owned by the whole file or something. Like, those are options. But I'm also want to, instead of thinking about the low-level details of how to organize the data structure for a minute, the other issue is if I have an edge crossing from one graph to another, does that actually help me? Because I would still have to, say I had B, C, D, E, and F in graph 2, A, Y, and Z in graph 1, and then all of the edges that are like those split edges, so the edges leaving A and the edges entering Y and Z, if they were stretched across both graphs, I would still end up having to delete them or pull A, Y, and Z over and then edit A, Y, and Z as well, right? Okay, so that's interesting. I think that suggests to me I don't actually want edges crossing graphs, even as an intermediate state. I don't know if that's a useful intermediate state, because in order to get it back to what you meant, you'd eventually want to delete that edge, and then you're not actually getting the automation of keeping the edge structure, right? You'd have to go in and manually delete the edge and reconstruct the edge the correct way for all of the edges that got dragged that way, right? That they got stretched that way. So I don't think that actually is useful. Now, another thing that popped up in my head going through that thought process, though, so we're going back to you don't have edges crossing graphs. But when I grab B, C, D, E, and F, and I copy them, or I cut them, and I paste them into graph 2, I was thinking you pop in dummy nodes. But I could also say, no, that's not what happens. And the reason I could say that is we could say the dummy nodes don't show up, the edges that were only half inside the graph do get lost. But this wouldn't actually be the end of the world, because the editor would still actually give you a good path. What you could also do is grab the whole graph of graph 1, including A, Y, and Z. Copy paste that, and then change the content manually of A, Y, and Z to the abstraction ports. And so if this was maybe this picture does have a flaw, which is the before graph, the graph 1 is actually identical in its topology to the after graph, the graph 2 of the after slide, right? Those two graphs have the same topology and almost the same content, but the reason that them having the same topology is a little bit of an issue is you could easily be in situations where that's not true, where what we have in graph 1 is the first half of a graph and there's more to it, but I didn't draw more to it. And when you went to do this reorganization where you're pulling out B, C, D, E, and F into graph 2, you would still you could still easily want to do that reorganization, right, on just those 5 nodes, and then you'd get into a situation where it isn't really the whole graph. So there's a tricky thing here where it could suggest that you'd always just copy the whole graph and trim it down. But imagine graph 1 was 10 times bigger, and this B, C, D, E, and F was the only piece we were trying to pull out to reuse. Then you wouldn't want to copy the whole thing and trim it down, because you'd be trimming down a bunch of it. It'd be much easier if you could copy A, B, C, D, E, F, Y, and Z, and then paste that into graph 2, and then modify A, Y, and Z, right? I think that could work. So one of those two options feels good enough to me, where you can... The only reason copying like that, the only reason the second option is a little worse is that it does not help you with the problem of what you'd really like, the best flow here, and the flow you get in like a text editor when the language also does not fight against you, is that you've got a block of code you're pulling out, and you cut that from its original location, paste it into the new place, decorate it with a function signature or something, you do just a little bit of changing, you put the new function call in place of where the old block was, and you're done, right? Whereas this, the flow would be like you copy the graph you care about plus the edges around it, the things around it that are structurally relevant to you, and paste it. And then you do the abstraction work. In this case, the abstraction work means modifying the content on those extreme beginning and end points of the graph to create the sort of logical ports. And then going back to the original one and then making a different selection, which is everything except the endpoints, and deleting them. And you see the slight difference there is that in the good mode, the selection that you make initially is good enough to do both the deletion and the pasting, so you can cut and paste. Whereas in the second one, you have to change your selection because you select more and delete less. And then the second selection is for the delete, which deletes a little less. And I think that suggests to me that the best model was the one I was sketching out first, not the one where you select the whole of graph 1 to do this operation, but the best one is where you select B, C, D, E, and F, and when you cut that and paste it, you get graph 2. Right, you paste it into an empty graph, you'd get something exactly like graph 2, except that the empty nodes of alpha, gamma, and lambda would require tiny touch-ups, which are equivalent to putting a return and a function signature around a block after you've pulled it out of a C code, out of a piece of C code. Then what would be left behind in graph 1 is a gap where that subgraph used to be, and you can see here where there might be a way that it's kind of annoying that you have to insert a new node called G2 and redo the wiring. But the wiring actually in graph 1 afterwards is completely different. Y and Z only have one incoming node, A only has one outgoing node, and that's because with the abstraction, we're saying that instead of encoding this directly into the graph, the compute model is going to do a little bit of the lifting here, And so, going into it, we only have one way to get into G2, which is to arrive at alpha, and the compute model will encode whether we're taking the B path or the C path. And getting out of graph 2, we have gamma and lambda, and there's 4 ways to get to gamma and lambda, but there's only 2 meaningful endings to the graph, and so G2 now has 2 outgoing arrows, right? So I don't know that there's actually a problem with the fact that it leaves a hole that you have to reconstruct, because that's like saying there's a function call you need to put here, and the new arrows are a part of the, instead of having a block of code, you have the name of the function is the G2, and the sort of having a return that you get and passing some parameters in might occasionally cause you to reorganize things around that just slightly. So I think that the reorganizing the inputs and outputs makes sense as a thing that you have to do manually. I don't think that that's really a big deal here, because you have to, like, the organization is quite different anyways, and I wouldn't feel that the tool was failing me by failing to infer this, because that is quite specific to the computation model, how that should be done. Okay, so I think I'm pretty happy with that story. So just to reiterate that so I can remember this for myself, the B, C, D, E, and F nodes get selected, you cut them. The paste into graph 2 is implemented as everything that got, all the content that was on the clipboard was the set of nodes, including their layouts, and the edges, that any edge that connected in or out to any of those nodes, any of those states, right? And that includes the edges that were only partially touching the selected graph, right? So we have the selected subgraph. Some of the edges that are connected to that subgraph are only half touching the subgraph, and the other half of the edge touches something else. When we paste, it constructs all that content, and where there are edges that are only half in the selection, what went into the clipboard was an empty node instead of a node with content to fill the role of the unselected sort of vertex where the edges come together. All right, so that's like 80% satisfying to me. And I say 80% because the open question here is, how does implementing that actually feel? Does it feel overly complicated? Does it feel a bit on the edge, or is it fine? Is it even good? I don't know. So that is a issue for a little bit later on in the project, when I'm set up a little better to answer how things feel in the visual editing. But I have that nailed down now, and I'm happy because it sounds like, from what I've seen just there, it seems like the way I chose to structure the abstractions should fit nicely with a reasonable flow for editing this visually. Now, I did say I would maybe take some time to look at how I'm doing this in the hacked editing. So let's just, maybe for 5 or 10 minutes. Let's try to keep it short. But I'm just curious if there's any ways that I'm, failing to take advantage of the structure of my current way of editing, that I could change it, so that I could change it maybe to make it a little easier to do this kind of reorganization move. Okay, so I've got hacked version of editing on both panels here. It's maybe a little different than what you've seen since previous brainstorming sessions. As I said, a lot has happened. There's now this idea of the directors are gone completely. We're attaching data, and we're also attaching these things called rules, and we're attaching them in this sort of declarative way. So this is the state, and then this data lives on this state, right? The attachments come after the declarations. And so, there's this enter rule. This is sort of preemptive and might end up being unhelpful. But for now, there's this idea of when you enter into a node, which can be a path or a state, that a chain of rules goes off. And the rules are implemented as function pointers plus 0 to 4 parameters that you pass to those, or that you can pass to those at the time you need to. Now, these are constant, so this kind of ends up working like a bytecode. This can't change. I can't put a variable here because this is going to actually be a topic that I need to spend more time on when we get back into the compute model stuff. But like, I am not running this over and over again. It's a one-time run. So it is not able to do anything in immediate mode. There can't be things here where I look at the game state, right? So this is becoming something like a bytecode here, but it's still just copyable data in that case, which is good, right? It's not like if it was immediate mode, then we would be building the graphs in a way that does not correspond to a serializable data structure, because I would be putting some of the structure of this graph's computation into C code itself, which is a little different from this, right? It would be in the execution of the C code at that point. No such problem here. But what I do have is, this annoying thing here where my states and paths are like this. Like I put all my states up here, my paths down here. So let's imagine, let's say I got dawn, morning, afternoon, evening. Okay. Maybe that is a good example of a pattern I would end up pulling out, right? Because you could imagine saying like, oh, we've got dawn, at morning, afternoon, evening, and dawn, morning here. And so this does not repeat exactly right here. But maybe we're going to have another couple of areas here and there in the game where you spend a full day in town going through the dawn, morning, afternoon, and evening phases. And so maybe you want to pull that out. Well, what would that look like? Let's just go through the act and see it for now. So it'd be like this. Let's say day in town.c. So this is setting up the new graph. This is the part that is equivalent to saying, give me a new graph. I gave it a name by doing that much work. Okay. Now I want to copy and paste, or rather I want to cut and paste. I want to cut this, and don't worry, it's all in version control. So if I screw it up here, I'll get it back by just reverting these changes later. So I cut this, and then I also need to do the paths. So I need to get all the paths that go from dawn 1, morning 1, afternoon, evening. Okay. Cut those. Okay. And there's also a path that goes into morning 1 here that I didn't get. So I also need to copy that over and cut it from here. So all the states that I removed here ended up here. All the paths that were connected to those states are destroyed here. So this still builds correctly, I assume. This one wouldn't build correctly. So let me zero this out. If I did this, is there anything left here? Oh yeah, this one is also belonging over here. So all of the edges, all the paths that are here that referenced any of these on either once or twice had to be removed from here and dropped into here. So that's these. Okay. What's going on here? What? This is weird. Something bad happened there that has nothing to do with this. Let me pause and figure out what happened. Okay, I'm back. Kind of strange. Looked like maybe Git corrupted one of my files somehow. One of the files was it was the same length it was before, but filled with null bytes after I checked out. Was just able to go back a version, grab a copy of the file, and fix it. Not sure how that is happening, though. Kind of weird. Anyway, what I've done is I've rolled back everything we did in the experiment up to the point of naming this. I didn't want to risk. This is the only point where I could sort of skip us to. So we've got the new graph set up, and we're going to copy over these states. So I want to grab these states, including the rule that goes with them. including the content that's on them. So I cut and paste those. By doing that, I should have broken all of the paths here. So this is slightly improved workflow. All the paths that were connected to these, even if they're only half connected, leave here. So those paths have been lost. Equivalent to how we are planning to do this in the visual version eventually. Now this isn't building because these are still referring to states that didn't move over. So we need to add in the like day begin, right? So this is like the alpha. This is the dummy that drops in here just to take a spot. And then we need some ends here. So there's end early wake up, and wake up. And so those will go here and here. That should let that build. And then what has to happen is another node. So we pulled out the node from here. So this state now is going to get day in town, right? And that's going to be, let's give this the control flow that it needs. So this is an ND rule 1. Upon enter, do a push of the graph day in town. So this is the reference to G2 basically from the picture. So we added the new node. We do need to redo the linking. So we have one incoming point day begin. That's going to be like arriving from there. So path Deriba intro connects to day in town. And so the difference here is the path. I do have to answer a new question, which I hadn't thought about. So this is good. Which is when I go to build the new path, I also might need to think about what data lives on these new paths. In this case, I think the way to think about it would be when I arrive here, I'm going to make a decision here in this string. The player is going to interact with the game interface, and the game interface is going to make the decision about how to advance here. And so all we need to do is set up the link from here to here. And when that happens, the additional decision about how to go into either early wake up or wake up will be made by that, maybe? I'm not sure. But I'm going to just make this a continued path. This is more getting into the compute model side. How should I design the compute model so that when I am done doing this transform that I think should be logical, it should be a sensible way to transform the data. How can the compute model support making this transformation of the data also give me the same results as the data before, right? Another way to put this is supposed to be a reorganization. The language designer, the computation model that is being applied to this data also matters because it needs to provide a way for this reorganization to actually maintain the meaning just as much as the data structure itself has to give an option for that. So this gives us that path going in. Now here we actually are kind of in a very similar case to the one I was drawing a picture of. We have two outgoing paths. So there's a path from day in town to dawn 2 called early wake up. And there's a path from day in town to morning 2 called wake up, right? And then the rest of what I haven't done here is the rest of the abstraction. So that's I've put the push here, but how are we going to actually arrange how are we going to arrange it so that when you take this path, you end up not in day begin, but in dawn 1 or morning 1, as you were supposed to originally? And how are we going to make it so that when you finish off with one of these, well, this one we know how to do, right? So this fits into the computation model as a pop with the corresponding code. But this would be like int from putter to you game move early wake up and wake up, right? So that would just pop this graph off the stack, dropping us back here, and then taking that code as the way to transition. The one we don't have in the computation model is the answer for how, when I put this now into the graph, how the path from here to here gets reorganized. Like, how, we used to have to walk the path by choosing one of these two choices, and now we have only one choice, and it's this, but we still want meaningfully these two choices to exist to the system too. Where did these go? Where did this come from? That is an unanswered question in the computation model, but outside the scope of this brainstorming session, I'm going to have to think about that. But to review, what I've learned from doing this here in the hacked content mode is that, at least at the level of the graph, there is a pretty good way to do it. It's not automatic as much as I would like it to be, but all I have to do is grab all of the relevant states and cut them from here and paste them to here, which is the same thing I would do on the visual version of the graph, making sure to grab the rules that were with them. Then the compiler can tell me where all the paths are here that have just busted, and then, so in a second operation, grab each of those and paste them into here. Then in another round, the compiler will tell me the paths over here that were only half rooted inside this subgraph and that need to have now port nodes or abstract nodes, or somehow need to be rewired up inside the new graph. And that I have to do manually, but at least I have the compiler to guide me towards doing the right thing at every step of the way, rather than me having to redo the wiring in my head manually. So that is good to know that this option exists right now as my option for how to pull something out from one graph and to form a new graph in the process. All right, this has been pretty useful for me. See you around for next time.